Welcome to lecture on cryptocurrencies. In this lecture, we'll see about cryptocurrencies, anonymity and pseudo-anonymity in cryptocurrencies, cryptographic hash functions, hash pointers and data structures, digital signatures, public key as identities, distributed consensus, consensus without identity, incentives and proof of work. Cryptocurrency. They are decentralized currencies, meaning that they are not governed by any central bank. Some cryptocurrencies are issued by developers or generated by the network algorithms. They are the digital assets, that means they are not tangible. Cryptocurrencies exist and operate on a blockchain where all the crypto transactions are getting recorded. Since it's stored in blockchain, the transactions are immutable and secure from tampering, counterfeit, and other forms of fraudulent transactions. These are the list of top cryptocurrencies such as Bitcoin, Ethereum, BNB, USD Coin, Bitcoin Cash, etc. Anonymity and pseudo-anonymity in cryptocurrencies. In crypto community, there is some level of either anonymity or pseudo-anonymity for security and privacy purposes. Anonymity will protect our real identity while pseudo-anonymity will just mask it. Though some transactions are anonymous to further criminal behavior, it is basic human right to protect their identity. Therefore, many find Bitcoin appealing because it has pseudo-anonymity built into the protocol. Anonymity is hiding whom you are. Pseudo-anonymity is giving an identity to the user but still protects who the real user is. Cryptography hash function. A hash function is a mathematical function that is used in cryptography. A typical hash function has a variable length input and returns a fixed length output. The hash functions are used for cryptocurrency, password security, and message security. The hash functions add security features to hash functions, making it more difficult to detect the content of the message or information about the recipients and senders. Cryptographic hash function. From the illustration in the left side, you can see when a message is applied to a hash function, it gives the digest message as output. So if the input can be of variable length, but when applied to a hash function, the output is of standard length. What are the requirements of hash functions? It can be applied to any size message m but produces a fixed length output h. It is easy to compute an output h which is equal to hash of the message for any message m. Given h, it is infeasible to find a message such that h of m is equal to h. This is the one-way property. Given an input, you will be getting the same output, but from the output, it is not possible to get the input. What is collision resistance? These two inputs giving the same output is called as collision. So the hash function is both weak collision resistance and strong collision resistance. So what is weak collision resistance is X is infeasible to find Y. Given X, it's not possible to find another message Y such that H of Y equal to H of X. And again, it is infeasible to find two messages X comma Y such that H of Y is equal to H of X. This is called as strong collision resistance. SHA-256 is one of the hash algorithms. How it works is the entire message will be divided into 512 bits block, and the first block of 512 bits is combined with 256 bits and given to a block. The hash function will be running and it gives a output. This output is again combined with next block and it gives an output. This continues so on until the final hash of 256 bits are arrived. This 256 bit of final hash is stored in the blockchain. What is a hash pointer and the data structure involved in it? A hash pointer is a pointer to where the data is stored, and along with the pointer, the cryptographic hash is also stored. So in a normal linked list, we'll be having a pointer, and this pointer will be pointing to the previous node, which is the address of the previous node. Here, along with the pointer, we also have the hash of the data. The hash of the data is calculated as shown in the previous slide. So a hash pointer consists of pointer to data along with the hash of the data. So you not only know the location of the data, but you are also able to validate the or verify the data. The hash pointer is used to build this blockchain or Merkle tree. So you can see in this illustration that like a regular linked list, you have a series of blocks connected to each other. But instead of a pointer, here you have the hash pointer. That is, every block, the data is group of transactions. So these transactions are considered as input and grouped together to get a hash value. So every block will store the hash value of the previous block. So that is how it is connected as a chain to the previous block. If you see here, the third block has the hash value of the second block. The second block will have the hash value of the first block. So if there is any change in the transaction stored in any block, immediately the hash, once you compute the hash with the changed transaction, this hash value will change. Yes? So normally whatever be the blocks that are after that block will be discarded. So any minor change, the hash value will be changed. Therefore, you will not be able to connect to the previous block. That's why it is tamper proof. Now we'll see what is a Merkle tree. Merkle tree is a binary tree formed by hash pointers. Every block, as I said, will be having few transactions. The size of a block is fixed. The number of transactions depending upon the size of the block can be stored in the block. A Merkle tree is constructed from the leaf node all the way to the Merkle root by grouping nodes in pairs. That is, two transactions are combined to form a hash. And you can refer to this illustration of Merkle tree. There is a transaction T1 and there is a transaction T2. Hash of T1 and hash of T2 are found. These two hashes are given as input to a new hash function and hash of 1, 2 is computed. Similarly, hash of transaction T3 and hash of T4 is found, and these three are combined together to form hash of 3, 4. Then hash 1, 2 and hash 3, 4 are given to a hash function and hash 1, 2, 3, 4 is computed. So you can see these are the transaction, these are the non-leaf nodes, and these are the leaf nodes, and this is the root node. So depending upon the number of transactions, the height of this tree will differ. So if any change in this transaction, if there is any change, immediately the hash value will also change. So if you try to make a change in T1, then H1 changes, H12 changes, and Merkle root also changes. So this particular transaction and the block in which this transaction is present will be removed. So this is a Merkle tree is a digital footprint of all the transactions that are stored in the block, because this Merkle root is stored in every block. So any change made to a transaction will change the Merkle root, and hence that transaction will not be accepted. From this illustration, you can find that Merkle tree also acts as proof of membership. If someone wants to prove that they have a particular data block which is a member of this Merkle tree, that is, they have a transaction that is stored in the block which is also connected to a Merkle tree. So we know that every block is connected to the previous block by means of the hash pointer. So if you present a block, if a transaction has to be validated, you present a block, then for validation, that particular block along with the previous blocks up to the Merkle tree. So only this a part of the Merkle tree is required to validate this particular data. The block and the relevant hashes stored until the Merkle root. So if you present this transaction and the Merkle root, it is possible to validate whether your transaction is present in this Merkle tree or not. Now let's see what is a digital signature. So we know that cryptography has built-in symmetric key and asymmetric key algorithms which are used for encryption and digital signatures. The digital signatures are cryptographic proof systems to establish trust. So it is basically used for three purposes. The first one is authentication, to ensure that the message is created by the sender. Non-repudiation, the sender cannot deny at a later stage that he hasn't sent the message. Third one is data integrity, the message has not been altered. So what is the process for signing? So initially the public key and private key will be generated. So for signing, a sender has to use his private key. So that is stands for non-repudiation. You can see to this data the hash function is applied. You get a hash value. To this hash value, the sender signs it with the help of the private key. He gets a signature. So along with the data, he also sends his signature. So that means the data has been digitally signed by the sender. So the receiver, how does the receiver verify that the sender has sent this digitally signed? So he does just the reverse process. So he gets the digitally signed data. So he will take the digital signature. The receiver knows the public key of the sender. So when he applies the public key of the sender, he will get a hash value. And he will also take the data and apply to the same hash function, and he gets a hash. So he compares these two hash, and these two hash, if they are same, that means it has been verified by the receiver. So what are the requirements for signature? So as we have seen, verify the public key, message, and sign with the private key and the message. So you need three things. You need public key, the message, and then digitally signed message. So it is not possible to forge anyone else's signature because the sender is signing with the private key. The receiver checks it with the sender's public key. Public key can act as identities. Having a public key as an identity means that you can use the public key as a reference. The digital signature will help this because it is used to verify the validity of the message. The idea here is to take the public key, one of those public verification keys from the digital signature scheme. That is, we have got certain algorithms to generate the public and private key pair. So from that pair, you are taking a public key and private key. You are signing with the private key and giving the public key to the recipient in order to counter verify. So here we already saw about pseudo anonymity. So this public key, it is like your email address or your account number. It serves as your identity, but at the same time, it doesn't reveal the actual identity. Yes, so whom you are, but people know what is your account number. We'll see what is decentralized identity management. So in case of, here we saw that the original identity is not revealed, but in a centralized environment, the identity can be verified. In a decentralized environment, to check your identity, we use addresses in case of Bitcoin cryptocurrencies. Each one is provided with the address. So your identity within this cryptocurrency Bitcoin network is your address. Your address is like your bank account numbers. And here when we consider privacy, the addresses are not directly connected to real world. They will not know whom I am, and they will know my account number, but they will not know to whom this account number belongs. How Bitcoin achieves this decentralization? What are the aspects of decentralization in Bitcoin? We should know or think who maintains this ledger of transactions. So it is not one single server, rather it is multiple entities with equal power. Who has the authority over which transactions are valid? Who will create the Bitcoin? Who determines how the rules of the system will change? How do Bitcoins acquire exchange value? So these are all the queries. So we should think whether it is centralized, or though we call it as decentralization, also it has a centralized component attached to it. So what are the aspects of Bitcoin to decide whether they fall in centralization or decentralization spectrum? So coming to peer-to-peer network. So as such, if you consider a cryptocurrency network, that means we are not fixing whom the nodes are. So there are multiple nodes, each one are given equal rights as each other. So it resembles the peer-to-peer decentralization system. And when talking about mining, so what is mining is, we saw about block, only the miner node will select a block that has to be attached to the blockchain. So the miner node is going to attach the block with the transaction to the blockchain. So when considering who is a miner, whether any peer node can act as a miner, no. So if we consider, there are some consensus algorithm, the winner of a consensus algorithm is going to be the winner of mining process. So here there is an aspect of centralization, because one node is going to be selected. It's not that everyone has equal opportunity. The one with more resources, the one with more computing power, so they emerge as winner. And how is the software getting updated? Is anyone maintaining the software, or it is maintained in decentralized manner? Yes, to speak about actually by principle of blockchain, it is maintained in decentralized manner. But however, this blockchain network is first created by some person who has created this particular cryptocurrency. So he would have created the Bitcoin software, and all other participant or peer nodes agreed to the contract or norms that has been written by the creator. So that's where there is an aspect of centralization, but still it works theoretically on a decentralization spectrum. What is distributed consensus protocol. We saw that the blockchain has got multiple peer-to-peer nodes. Yes? So in order to validate a transaction and then validate a block that has to be attached to the blockchain, a distributed consensus algorithm is run. All the peer nodes will be running a algorithm in order to emerge as a winner. So the requirements of distributed consensus are this consensus algorithm should terminate within a finite time and the output must be same. That is, when a consensus algorithm is run, if 5 nodes are running, the output must be same for all the 5 nodes. The value should be a value that was proposed as input by at least one of these correct nodes. So the transaction must be proposed by at least one of these nodes. We'll see what are incentives and rewards and why it is required. So here we saw that there is a need for transaction validation. There is a need for block validation. Why should the peer-to-peer node do this validation if at all they don't get any reward? We know that such cryptographic networks or cryptocurrency networks, they have some cryptocurrency involved. So in order to validate the transaction, they should give reward to the peer nodes or participation of the blockchain nodes. So there is a minor reward. So whoever emerges as a winner or miner after running the consensus algorithm, they will be given a block free. And so the block fee initially it will be determined as certain amount while creation of a block. So the transaction fee is given for validating a transaction. So here, since cryptocurrency is involved, you can give a part of the cryptocurrency whoever performs this validation. How this consensus works without any identity. There is a need for identity. Some protocols need identity, but as we saw, the Bitcoin nodes, do they have identity? Yes, they have pseudo anonymity, but still it is possible to have identification. The actual identity is hard in peer-to-peer system because there is no central authority who will assign this identity. So here the pseudo anonymity is the final solution. As this works well, people using cryptocurrency, Bitcoin and other blockchain networks, they are comfortable with using this network. What is a consensus algorithm or how does this algorithm works? First, there is a transaction. The transaction can be like X transferring some A dollars to Y, or there can be an assert. So this is a transaction. So anyone who creates a transaction and wants to store it in a blockchain will broadcast the transaction to all the peer nodes. So every node will try to collect the new transaction and they will form a block. There will be number of transactions. Unlike the traditional databases, a block will not have records of same type. It can be different transactions of different types grouped together to form a block. So in every round, a random node will broadcast the block. Other nodes will accept the block only if the transactions inside the block are valid. We saw how the transactions are getting validated using the Merkle tree. Then the node, if they find that all the transactions in a block has been validated, they will express their acceptance of the block by including the hash in the next block they create, so that the subsequent block is getting attached to the blockchain. What is proof of work? We saw that there are number of peer nodes. Why should they validate? Because they are getting the transaction fee and mining reward, which is a really huge amount. So here there is some consensus algorithm, and the winner of the consensus algorithm gets the right to add their block to the blockchain, and finally they get the block reward. So in order to run this consensus algorithm, we have one algorithm which is called as proof of work. So in proof of work, the algorithm is run, and every participating node will spend their computation power, their electricity to calculate a particular value so that they emerge as winner. So the one who finds the output value first will emerge as a winner of this proof of work, and they will get the chance to attach the block to the blockchain and in turn receive the block reward. So you can see what is a hash puzzle. So what is the computation that is actually done by the miner node by running the proof of work consensus algorithm. So in every block there will be a header which has got a difficulty target and a nonce value. So once you set a difficulty target, according to this, the nonce value will be set. The nonce value has certain number of leading zeros. The more the number of leading zeros, the more difficult it is to find the nonce. So you set a difficulty target that so that within certain time the nonce value could be found. That is, at least it will take some 10 minutes to find a nonce value depending upon the difficulty target given a high computation mission. So we perform the hash of nonce value, previous hash, and all the transactions. So this is how the hash puzzle has to be solved. So what are the properties of proof of work? So this consensus algorithm, it shouldn't be very easy. It should be difficult to compute. If it is very easy, there will be more number of hackers. So once it becomes difficult to compute, they need to spend lot of money in because of electricity and computing power. So the second one is the cost must be parameterized. That is, it nodes automatically will recalculate the difficulty target every 2 weeks so that that particular nonce can be computed. So initially it will be difficult to find. So later when the time reduces, you increase the difficulty target so that it takes at least 10 minutes to compute the nonce. So it must be also very trivial to verify. The nonce must be published as a part of the block. The block has certain header part in which the nonce is present. So once this nonce is found, the hash of all the value will be found and the target can be calculated. So what can a malicious node do? How can they cheat the blockchain? So I am having some $50. So I am authenticated and that $50 belong to me. We have an issue which we call it as double spending. That is, it is only a cryptocurrency. That means it is stored in a digital form. So this $50 I can send to X and still I can claim that I'm having $50 and the same $50 I can also send to Y. So this is called as double spending attack. You can see here the sender is A. So it has got few dollars. It is signed by A and paid to B. So using its private key, it is signing and then paying that dollars to B, and this transaction is being recorded in a block of the blockchain that the amount has been transferred to B. Now the same A is also sending the same $50 to A dash. So it is also using the same private key and also sending this and saving the transaction in an other block. Now these two transactions, it is double spending. A is spending to B as well as A is spending to A dash. Yes. Now how can this be prevented? Yes. Any fault transaction, we saw that it can go and be validated. Say when A says that it wants to transfer $50 to B, during transaction validation, initially every node will be able to move across the Merkle tree to find if at all A has $50. Now it can validate that A has $50. What if A gives the same $50 to two recipients? So here the first transaction is stored in one block, the second transaction is stored in another block. From Bob, in merchant's point of view, you can see this block, every block we saw that there is transaction validation and then block validation. So this transaction of A to B has been validated and is present in 3 blocks. But this transfer of $50 to A dash has been verified and stored only in one block. So whichever is the longest chain, that will be considered. So because when this is considered and the transaction is recorded in the block, that means there are 3 confirmations that A has got $50 and has been transferred to B. But there is only one confirmation that A is having $50 and has transferred to A dash. So wherever there is more number of confirmation, that will be taken. So when this transaction is validated, entered into a block and attached to the blockchain, then automatically this validation cannot happen after this, because now this has been validated. So this will be considered as a new transaction. Now the block validation can confirm that A doesn't have 50 more dollars. So this is how double spending can be prevented. We saw that the block reward is given to the person or the node that has validated a block and has attached a block to the blockchain. So how this block reward is generated? Initially, the creator of the block will have the special coin creation transaction as soft coded. So it will be generated and this amount will be transferred to the recipient. The value of this is fixed like 25 Bitcoin and it will be reduced after every 4 years. So initially for this validation, the amount will be more. For subsequent validation, after a certain period, it will be reduced. The block creator will be able to collect the reward only if the block has been attached to the blockchain. How does one receive a transaction fee for validation? Suppose I am transferring $50 to B, then my input amount should be $50. So instead of $50, I should have it as $51, so that out of this $51, $50 will be transferred to B and that remaining $1 will be given as a transaction fee to the one who had validated that particular transaction. These are few of the case studies and references. Thank you for listening to the video.